Welcome guys. This is the lecture 2 on chapter number 9, and I would start by talking about the highlights of the previous lecture. So we had started talking about probabilities involving two lives in chapter number 8, and then we had discussed in the previous chapter the probabilities relating to the situations where the order of death is important. Okay, so first of all, there were these two formulas that this is the probability that X dies within n years and he is the first one to die out of the two. So this is just the probability going from 0 to n, probability that X lives till some arbitrary time t and then he dies. And at this time t, I want Y to be alive. Okay, so Y is alive and X dies at this time, and I add up all these times t from 0 to n, right? So that's what happens here. And then I had the probability that X dies within n years and he's the second one to die. So this is just the probability that X lives till time t, some arbitrary time t, and then dies. Okay, and he's dying here, and at this moment I want Y to be dead already, so his death is the second one, right? Makes sense. Okay, then I had discussed two properties with you based on these formulas. So if you add both of these probabilities, it is the probability that X dies the first plus the probability X dies the second within n years. So this is just the probability that X dies within n years and the order does not matter. Okay, and then I had discussed this formula that if X the probability nqxy2 and the probability nqx1y, the difference between these two is only that is only this term. Okay, and this probability is saying that y dies second and he has and Y dies second and he has to die within n years, and this probability says that X dies first and he has to die within n years. Okay, so the difference between these two is just the case where X dies within n years and Y survives beyond n years. Okay, so we just want to eliminate this case, and then these two probabilities become the same, and I've given the reasoning and explanation for this already. Okay, and then I had taken the case where both of the lives were independent and identically distributed. Okay, so under that case, nqx1x, that is both identical life, one of them dying first is just half times the probability, is half times the joint probability of death. Okay, so I'm just halving the probability of first death. This is the probability of first death, right? First death occurring within n years. That is what the joint death probability is, right? And since I want a particular person's death to be the first one within n years, and both the deaths are similarly, that is identically distributed, I just take the half of it, right? So that makes sense. And since this one nqx2x, now here I want the second death's probability and I want a particular person to die the second, so I just half the probability of second death. So failure of the last survivor status is nothing but the probability of second death, and it has to occur within n years. So I'm just halving it because I want it to happen for one of the two people, right? So a 1 by 2 here, and I can actually evaluate this in the form of single plus single minus joint. Okay, or another very convenient way of evaluating these probabilities is that we take the half of, now nqxx, we have got the last survivor status. So this just means that both of x and x die by time n, right? Because if either one survives uh, that long, the last survivor status would be active. So I can write this as nqx into nqx, right? Or you can just write this as half into nqx square. So this method usually comes out to be easier as we are talking about last survivor status type probabilities, right? So you can use this formula usually. This one is actually uh, quite inconvenient because then you'll have to convert everything in terms of p probability. So I would suggest you to use this one. So these are a few things we discussed. Now I'm going to discuss a question relating to it, which I gave you as an assignment in the last part, so that things become clear to you. So let's just discuss this one question that is given in the co-reading. This is question number 9.5. Okay, so question number 9.5 is what we're discussing, and it asks us to use the AM92 ultimate mortality tables. Okay, and it wants us to calculate 5Q 40 to 40, right? And the reason behind actually using AM92 here is that see, in AM92 we are only talking about one life, that the gender based selection is not happening in case of AM92 tables, right? So there is no discrimination between the male and the female mortality. Okay, so here actually when they have taken two lives, we have to assume them to be identically distributed because they are of the same age. So that's the rationale behind taking EM92. Whenever they will be talking about identically distributed lives, they will mostly take EM92 tables, and whenever they will be talking about two different lives, one husband and the other wife, they will be taking the PMA tables. Okay, PMA92, the PMA92 male, and the PFA92 tables, right? So there are these tables which they take when they want to talk about separate lives. So for evaluating this one, I do nothing. This is very easy. This is just the half of, because I want it to be in the order, half of 5Q 40 40, right? So since I'm talking about the second life, I have to take the last survivor status, and it has to fail within 5 years, and for one life, right? For a particular life, so I have to take the half of it. So this just becomes half of 5Q40 into 5Q40, right? That's how you evaluate it. So this becomes a half of 5Q40 squared, right? Now I can just put the value of this thing and get the answer. So that just becomes half of 5Q40 is just 1 minus L45 over L40. Okay, right? And this thing squared, so this would get you 0.000016 if you copy the value from the table, right? So that's how you evaluate these things, right? So that was all about the revision from the last part, and now I will move on to a new topic. Okay, so let's just start talking about the contracts relating to these probabilities. So I had already told you in section 1 that we will be talking about two types of contracts in broad categories. The first one are contingent assurances, and the other ones are reversionary annuities, as the name of the chapter suggests. Okay, so firstly I'm starting with contingent assurances. What are they? Their present value random variable, the EPVs, and I think I'll be discussing the variances too, right? So all these things relating to contingent assurances. Okay, so the first type of contract I want to discuss now, these contracts, they will be depending upon the death of one life, provided that the other life is alive or dead, or they would be depending upon the order of death, right? So that is what I want. Okay, so the first type of contract I'm discussing is this. Okay, there's this contract issued to X and Y at inception at time 0 till time infinity. Okay, so am issuing a whole life contingent assurance, where the condition is that an amount of £1 would be paid if paid at the death of X. £1 is paid at the death of X, provided that, and immediately at the death of X, not at the end of year. So let's write it as immediately. It can also be at the end of the year, no problem about that. £1 is paid immediately at the death of X, provided that that X is the first one to die. So provided that Y is still alive, that is what I want, right? If y would still be alive, x's death would be the first one to occur. Okay, so I will be paying the amount at certain time t. Okay, this time t, depending on the condition that x dies as at this immediate time t and y is alive at this time t. So how will I represent the present value random variable? Okay, let's just see that. Okay, so the present value random variable for this contract is v to the power of tx if tx is less than ty, less than equal to ty, and 0 if tx is greater than ty. So what is happening here? All this is saying is that if x is the first one to die, that is the lifetime of x is less than the lifetime of y, then I pay a payment of 1 and I discount it for the lifetime of x, that is tx, right? So it is discounted by the random variable of the lifetime of x. So I discount it for tx years. Okay, that is the lifetime of x, because this payment is paid at the death of x. Okay, and this happens only if the lifetime of x is less than lifetime of y. If the lifetime of x is greater than the lifetime of y, that is if x dies after y, that is that x's death is the second to occur, then there is no payment, so 0, right? So it makes a lot of sense. And if I talk about the expected present value of this contract, okay, so if I talk about the expected present value, since this is a continuous random variable, I've taken tx, not kx, so I'll be talking in terms of integral. So there would be a t which would go from um, 0 to infinity, okay, v to the power of t, that is the present value, okay, tpx into mu x plus t, because the amount is payable on the death of x, right? And at this time I want a certain thing for y. The thing I want for y is for y to be alive, so tpy dt. So this is your expected present value. All this is saying is that x would receive an at the death of x we would receive an amount of £1. Okay, and when is this amount payable? This amount is payable at time t. So x has to live till time t first and then by die at exactly at time t where y has to be alive, right? And at this time there would be a certain payment of £1 which would be discounted back to time 0, so with the factor vt, and this t can take any value between 0 and infinity since this is a whole life contract, right? So that makes a lot of sense. That is how you construct the EPV of this contract. Okay, if I go on and talk about the variance of this contract, if I go on to talk about variance, variance of this contract would be expected present value square minus expected present value whole square. So the symbol for this contract is written as a continuous, a immediate, that is this payment is happening immediately on the death of x, x1y, because I want x's death to be the first one, right? So that's a symbol. If I talk about this contract, this can be written as obviously 2a x1y minus a immediate x1y whole square, like we write any other variance where this part of the thing, this is evaluated as going from 0 to infinity. It's the exactly the same as this, but the interest factor or the discounting factor is squared, so this becomes v to the power of 2t tpx into mu x plus t into tpy into dt, right? So I just squared up the discounting factor. So that is how it works, accepting that it's all the same. So this is how you can calculate the variance of this contract, and this is how you calculate the EPV. Often what they do is, instead of writing this entire thing, they multiply this TPX and TPY to make it one term, that is TPXY, because we know that TPXY is equals to TPX into TPY. So you can also do that. You can write this as, instead of these two terms, you can write it as TPXY, the way they have done in the co-reading material. Cool. All this means is the same thing, that I want x to live till time t, then I want him to die immediately, and then at this time y should be alive, and then I have to pay make an amount of £1, pay an amount of £1, and then this would be discounted 2 times 0 with the factor vt, and this t can be between 0 and infinity. So that those are all the things I want. So that's the intuitive reasoning behind this kind of a EPV, right? So makes sense. Well, let's move on to the next type of the contract. Next thing I can have is AXY1, okay, which can be written as, this is the EPV, of course. Okay, I'm not going to discuss the present value random variable. Okay, let's do that too. Let's discuss the present value random variable too. Okay, so the present value of random variable of this contract, that is the one which pays which makes a payment of £1 on the death of y, provided that y's death is the first one. Okay, so going from 0 to infinity, I want the life aged y's death to be the first one. So I want ty to be less than tx, that is when I'll be making the payment less than equal to, and I want if ty is greater than tx, there would be no payment. Okay, 0, and in this case there would be a payment of £1. Okay, so if I write the present value random variable, what would it be? It would be equal to v to the power of ty, because the payment is made at the death of y, so it would be discounted by this factor, that is the lifetime of y, and this is when ty is less than equal to tx, and otherwise it is 0, ty is greater than. Okay, that is how you evaluate this. And if you want to write the EPV, the actual symbol is a immediate x y with 1 over y, of course, and it would be going from 0 to infinity, v to the power of t into tpxy into, now I want mu y plus t dt. And how do you read this? You read this as, I want okay, let's just separate these two in order to read this, tpx into tpy, that's what it is. Okay, so what I want is, I want y to live till time t, and then I want him to die immediately. Okay, him or her, and then at this time the condition is x should be alive, so there would be a payment if all these things happen, and that payment would be of £1, which would be discounted back till time 0, and this t can take any value from 0 to infinity. Okay, so that is the rationale. Now they have given this little conditioning in the core reading, a little proof. Okay, so the proof is of what? The proof asks us to prove that ax1y plus axy1, these two things, these are equal to axy. That is a payment which is made on the first death of x or y. And if you see, the intuitive logic behind this is actually very apparent. See, all this is saying is that £1 is paid at the death of x if x is the first one to die. Okay, and all this is saying is £1 is paid at the death of y if y is the first one to die. So whoever's death is first, we pay £1, and that is all this is saying, pay £1 on the first death of x and y. So these should be equal. Let's just do the proof. So going from 0 to infinity, this is just tpxy mu x plus t v to the power of t, right, dt, because I want x to die, I want y to survive, and I want this to be discounted back till time 0. Okay, plus going from 0 to infinity, this is just tpxy again, mu y plus t this time. Okay, and vt dt. Okay, so if I add these two, because here I want y to die, right? So if I add these two, this becomes 0 to infinity tpxy mu x plus t plus mu y plus t. Okay, these two add up, vt dt, which is, if you go back, turn back your pages to the previous chapter and check, this is the same as the definition of axy, because obviously immediate, because all this is saying is that I want both of x and y to survive till time t, and then one of them to die, that is the first death. So if one of them die, I pay an amount of £1, which is discounted by a factor of Vt, and this t can take any value from 0 to infinity, right? So this makes sense. So I actually, this is what I want. So these two things are actually equal. Cool. Okay, if I come to talk about a different contract, let's talk about the third type of a contract. Here the condition is that I pay on the death of £1 on the death of X if X is the second to die, or you can also write this as if Y is already dead. So I pay £1 on the death of X if Y is already dead. So if you try to perceive the present value random variable of this thing, see, I would be paying £1 on the death of X, that is V to the power of Tx. That is how it would be discounted, right? So that's what happens, and this happens only if Tx is greater than Ty, right? That is X has to be the second one to die, and 0 if Ty is greater than Tx. So that is Tx is less than equal to Ty. Okay, so that's your given condition. And if I talk about the EPV of this contract, EPV turns out to be going from 0 to infinity. What do I want? I want X to die at a certain time t, so that just becomes TPX mu X plus T. Okay, and at this time Y should already be dead, so TQY. Okay, and then there's just Vt because I want to discount it back to time 0. Okay, and Dt. So that is what the definition would be. And if I talk about and if I talk about the symbol for this, this would be AX2Y, right? And if I talk about the variance of this contract, this becomes 2AX2Y minus AX2Y whole squared, right? And here only this factor, this interest term, instead of this it becomes V to the power of 2t. Cool. So that is how it works. This discounting term changes and everything else is the same. So this should all intuitively be very logical to you, right? That's how things work. I hope I'm not going too fast. If I am, you can just slow down the video, or you can I don't know, go back and check it again, because I'm explaining everything here. It's just that things are very repetitive, so I'm going fast with them. Okay. So if I talk about a similar contract for Y, where £1 is payable, this is the fourth type of contract. £1 is payable on death of Y if X is already dead. That is Y is the second one to die. So what does this become? This just becomes PV would be equal to V to the power of Ty if Ty is greater than Tx, and V to the power of just 0 if Ty is less than equal to Tx, right? And if I talk about the EPV, that just becomes going from 0 to infinity. What do I want? I want TPY, that is I want Y to live till time t, and then Y can die at time t, and X should already be dead, TQX, and then V to the power of T to discount dt, right? And T can go from 0 to infinity. And variance, and this is obviously denoted as AY AX 2 over Y, right? So, and the variance is 2AXY2 minus AXY2 whole square. So that's how you can evaluate all these things, right? And okay, and there is one more little proof here. Okay, the proof for this is given on page number 11. Okay, and this is saying that AX is equal to AX1Y plus ax2y, right? So that is the other proof. So all this is saying is that this is the EPV of a payment of £1 on the death of X. Okay, and this is the EPV of payment of £1 on death of X if he dies first. And this is the EPV of £1 on the death of X if he dies second. So all this is saying is that these two things are equal, because with here we cover the probability of X dying first and making a payment on his death, and this covers the probability of X dying second and making a payment on his death. So these two probabilities just add, these two EPVs just add up to the EPV where £1 is paid at the death of X, no matter if he dies first or second. Cool. So that is what I want here. Okay, very well. Let's just look at the um, let's just look at the proof. So I'm starting from the RHS. Obviously, RHS says ax1y plus ax2y. So this just becomes going from 0 to infinity v to the power of t tpx and mu x plus t into tpy dt, and plus going from 0 to infinity v to the power of t tpx, that is I want him to live, and then I want him to die, but y should already be dead by this time, so dt, right? And here he should have been alive by this time. So if I add these two, let's just add these two, so it becomes going from 0 to infinity v to the power of t is common, tpx is common, mu x plus t is common, what is not common is tpy plus tqy dt, right? So these two add up, and I know what this is equal to. This is equal to 1, so it doesn't even exist anymore. And I have got 0 to infinity v to the power of t tpx mu x plus t dt. So that's just ax, obviously immediate. So that is what I just proved, right? And it logically made sense too. Okay. There are a few more things. Here now I will assume the lives to be independently and identically distributed. So identical lives. That is, we would be using AM92 when they give us such questions. If they say so, obviously they'll say AM92 in most of these cases. Okay, so the proof is, the third proof is AX1 x is equals to half of AXX, immediate obviously. Okay, so so how do I prove this? See, I already know that immediate x 1y plus a immediate x y1 is equal to a immediate xy. This means that the EPV of £1 made at the first death of X plus the EPV of £1 made at the first death of Y is equal to the EPV of £1 when the payment is made at the first death of X or Y, doesn't matter. Okay, so that is what this is saying. So if I replace this by identical lives, this just becomes a immediate x1x plus a immediate xx1, okay, is equal to a immediate xx, and these two are the same thing, so this can be written as 2 times a immediate x1x is equals to a immediate xx. So I can just write it as a immediate x1x is equals to half of a immediate xx. And this is similar, very similar to that property we had discussed for the queues, right? That were the death probabilities. They said that nq x 1x is equals to half of nqxx. So all this is saying is that nqx1x, that is when we want a particular life to be the first one to die, it's just half of the joint life probability or the EPV. In this case it was the probability, and in this case it is the EPV, right? So all this is saying is because I want the payment to be made at the first death, and when I want this to be for a particular life, when both the lives are exactly the same, when both of them are exactly the same, I'm just expecting half the amount of payment, right? So that should make sense, and it was the same logic for the EPV, right? And there is a fourth one. Okay, there is a fourth proof we need here. Let's just talk about that. So the fourth proof is a x2 x is equal to half of a immediate xx. Okay, how do I get to proving this? Well, let's see. Okay, so if I would have talked about two separate lives which were not identical, if I talk about a x 2y plus a x y2, what would this have been? Going from 0 to infinity, let's just prove this first and then I'll get to proving this. So this would be going from 0 to infinity, dpx into mu x plus t, that is I want x to die and I want y to be dead already. So this is just tqy, okay, and v to the power of t dt, right? Plus what I want is going from 0 to infinity, t py mu y plus t into, I have this thing, it just becomes t qx into vtdt, right? So that is what I have, and I have tq, here I have got tqx, and here I have tpx, and here I have tqy, and here I have tpy. So this is a lot of confusion here. Okay, so let's just try to solve this. This becomes going from 0 to infinity. This becomes the v to the power of t is common. That is the only thing that is common. This one I can actually write it as, let's write everything in terms of q probabilities, okay, or maybe let's just make them p probabilities. Okay, let's write everything in terms of p probabilities. This becomes tpx mu x plus t into 1 minus tpy, okay, plus tpy into mu y plus t into 1 minus tpx. Okay, so this is what I have here, and obviously a dt, and with okay, yeah, so that's what I have. Let's just try to solve this and get something out of it. So this goes from 0 to infinity, v to the power of t, and tpx into mu x plus t, okay, into 1, that's why I'm leaving it, minus, obviously the vt is there, so there is going from 0 to infinity vt, into tpx into tpy into mu x plus t, okay, that's what I have, and till here I'm done. And for the remaining part, I've got a plus going from 0 to infinity, vt is there, yes, tpy into mu y plus t, okay, this is something I have, minus going from 0 to infinity, v to the power of t into tpy into tpx into mu y plus t. Okay, let's just try to see these things. See this here, this thing is ax, right? That's what I have, and this thing here is ay. So plus y, and minus what I have is going from 0 to infinity e to the power of t tpxy, because both of them have tpx and tpy, mu x plus t plus mu y plus t, and a dt here. See what has happened. Where have we reached? We have reached this thing as a xy, because that is what this is, the probability that x and y both survive till time t, then either one of them dies and then there is a payment. So I want the payment to be at the first death. So this is just ax plus ay minus axy. And what was I calculating the result of? I always forget what had I started with. Right, these two. So this becomes ax2y plus axy2 is equal to this thing. And this thing you should remember from the previous chapter. This is just single plus single minus joint. So I can actually write this as ax2y plus axy2 is equal to axy to the power of it. Right? Okay. So I've got this result. Right? And now I need to analyze it. This means that the payment is made at the second death of x. This means that EPV when the payment is made at the second death of y, and if I add them up, this just gives me the EP when the payment is made at the second death of x or y, no matter whom, but at the second death, right? So this is something I can conclude, and if both of these are lives are identical, this becomes ax2x plus axx2 is equal to ax, and this becomes 2 times ax2x is equals to axx, right? And if I send this thing on the other side of the aisle, or the equal to sign, whatever you call it, becomes half of ax. Cool. So that's what I have, right? So this is my result that I wanted to prove, result number 4. Okay, so all the formulas and the proofs we have discussed so far, they actually were applicable when the payments were made immediately on death and not at the end of the year of death, right? But they can be applied as it is to lives when the payment is made at the end of the year of death. For example, I can actually write ax1y, that is when the payments are made at the end of the year of death, into 1 plus I to the power of half times, and this is equal to a immediate x1y, right? So I can actually make transformations for all the contracts we have discussed. But if you want to transform this into this, right, so you just send this on the other side, so this just becomes a x1y is equal to a immediate x1y into 1 plus I to the power of minus half, right? So all the this is the way we can transform these probabilities, and actually all the properties we just discussed, they are applicable on both of them, right? They are also applicable when payments are made at the end of the year of death. So if I go back and see what all properties we have discussed, see this property I had discussed for immediate ones. Sorry, forgot to put this. So this property is also applicable for when payments are made at the end of the year of death. That is, a x2x is half of a xx. This is obviously the last survivor status, and the logic behind this is that in this case I want the payment to be made at the second death of this particular life x, and in this case I wanted the EPV of the payment when it is made on the second death. Okay, so when I'm fixing it onto a particular life, out of the two, this becomes 1 upon 2, because both of the lives are exactly identically distributed. So this formula also implies that ax2x is equals to half of ax, right? So these are also applicable for payments made at the end of the year of death, and this formula also I forgot is also applicable when payments are made at the end of the year of death, and all of these are applicable. So you can actually go back in your notebooks and check whatever I've discussed. Okay, so that's all for this video. Let's just take the annuities up in the next one. Okay, this was too much for you to process too. And if you're getting bothered that why are we taking only symbolical examples and no numbers, actually I'll be um, solving the revision notes in the revision notes video, where we'll be only taking up the numerical examples. So right now I want to understand the algebra behind everything, right? Then we'll get to the numerics of it, the application of these things. So I think I'll be able to finish this chapter in 2 to 3 more videos. I think two would do, right? Two small videos, and then we'll get to the real game, that is the revision notes.